All right, let's get started. Welcome to week 3 of CS294-112, Deep Reinforcement Learning. So today I'm going to talk about learning dynamical system models from data. I'll get into this in a moment, but first a few announcements. So we posted the assignment for the final project on the course on the Piazza yesterday. So the final project milestone and so on is not until the end of the semester, but we wanted to post it early so that you guys could take a look at it. Start forming groups if you want to work in groups for the final project. If you want to ask us about whether or not your idea for the final project makes sense, you're welcome to do that as well. So do try to get started on that early. The milestone and so on is not until after all the 4 main homework assignments are over, but you are definitely strongly encouraged to start on your final project early and certainly start forming groups and so on. And then homework 1 will be posted today, so we'll have all those materials up shortly, and that will be due in 2 weeks. All right, so let's start with today's lecture. So last week we learned about how we can acquire sequential decision-making policies by learning to imitate a human demonstrator, and then we talked about how if we don't have data from a human, we could actually use optimal control or planning techniques to figure out how to autonomously choose optimal actions. So it has this kind of flavor of back-propagating or planning through a known dynamical system. For example, if you know how the laws of physics govern your autonomous vehicle, you could back-propagate through those equations of motion and figure out which actions you should take. So today we're going to talk about what happens if you don't know the dynamics of your system. So for some systems, identifying the equations of motion is very easy, and for some, it's exceptionally difficult. So today we're going to talk about also a lot of more standard control stuff as well as model-based RL. So we'll talk about fitting global dynamics models, fitting local dynamics models if fitting global dynamics is infeasible. And then on Wednesday, we're going to put it all together and actually talk about how we can combine model learning and optimal control and imitation learning to actually autonomously acquire policies by essentially imitating optimal control so that we can train these deep neural network policies. And that's going to put together a lot of the pieces that we've learned. And towards the end of this lecture, I'll kind of discuss how this turns out to, even though it seems a little weird, turns out to be a very natural solution once you consider the entire model-based RL pipeline. Okay, so what's wrong with known dynamics? Why is all the stuff that we learned last Wednesday not enough to solve all of our problems? Well, so for some systems like, for example, cars or aircraft, oftentimes we have a pretty good idea of how their motion is affected by the actions that they take. We might have very good equations of motion written down. You know, for a car, you pretty much know if you turn the steering wheel to the left, the car will go left, and so on. But there are other systems for which known models of dynamics are very difficult to construct. So in particular, this often comes up in things like robotic manipulation, where you have really complicated physical phenomena like deformable objects, context, and so on. But it also comes up in a range of other fields. So if for example, you have an agent that interacts with human users, for example, it's a part of a website or some other interactive system, well, maybe those human users are actually kind of unpredictable and a little tough to model. So there are a lot of situations where you might not know exactly how the state in action leads to the next state, and you'd like to have an algorithm that can still handle that. So in this lecture, we're going to talk about actually learning the model of the dynamics so that we can then use all the optimal control or planning tools that we discussed last week. So here's a summary of today's lecture. So I'm going to start with an overview of model-based reinforcement learning. I'm going to talk about first situations where you just learn the model and then apply some of the optimal control tools from last week. I'll also talk about situations where we might simultaneously learn a model and a policy, so we can actually learn the model, back-propagate through that model into the policy, and actually get a policy directly. And I'm going to talk about some of the strengths and weaknesses of these two approaches. I'm going to discuss the distinction between what's called global models and local models. So global models are a model of physics for the entire environment, whereas a local model is just a model in the vicinity of the states that you're currently visiting. And I'm going to talk about why you might want to do one or the other. This order here is a little reversed, but before I talk about that, I'm going to talk about what kind of models we can use, so what kind of representations, whether it's deep networks or something else. I'm going to talk on the topic of local models. I'm going to talk about learning local models with trust regions, and this will be some mathematical tools that we'll also use later on in the course where we talk about model-free learning with trust regions, so that'll be really useful to know about. And so here are the goals for today's lecture. Understand the terminology and formulas of model-based RL so that when someone says model-based RL, you basically know what they're talking about. Understand the options for the models that we can use in model-based RL. So deep neural network models are a good choice of model, but there are also other good choices, and it's important to understand their strengths and weaknesses. And then understand some of the practical considerations of model learning. You know, why might model learning be difficult? Why might model-free algorithms that we'll learn about in subsequent weeks be preferred in some situations, and why not? So these are things that hopefully you'll get out of today's lecture. All right. So why might we want to learn the model? Why might we want to try to figure out how the current state in action affects the next state? Well, the short answer, very simple, based on the stuff we discussed last week, is that if you have this optimal control problem, this is exactly what we saw last week, and you want to perform this minimization, you need derivatives. You need derivatives of the cost, and you need derivatives of the dynamics. Derivatives of the cost usually are fairly straightforward, but the derivatives of the dynamics, that's what requires that model. So if we learn the model, we can differentiate through it, and then we can apply all of our favorite optimal control rules if we're in the kind of the continuous realm. If we're in the discrete setting, like in the Monte Carlo tree search case last Wednesday, same deal. In order to perform these forward predictions, in order to determine the relative value at each node, you need to actually know how the world is going to be affected by your actions. And since you need to try multiple actions from each state, since you can't rewind the real world, you really need a model of the system in order to do this. So if you can learn a model of the system, you can either differentiate through it to get these derivatives and apply all of our favorite optimal control procedures, or you can simply use it for prediction and apply all of our favorite planning algorithms, like the ones we learned about last week. So these are reasons why we might want to learn the model. So if we knew this dynamics function, we could use the tools from last week. And I'm going to, for a lot of today's lecture, I'm going to kind of refer to deterministic dynamics. I'm going to say, f of x comma u is equal to xt plus 1. But in general, remember that this might also be a probability distribution. So for, in general, we typically would have a probability distribution. And if we're in a continuous setting and we want to be kind of, we want to keep it simple, we might say maybe it's a Gaussian distribution where the mean is given by this f of x. Or we can just talk about deterministic stuff, but keep in mind that the stochastic extension is usually pretty straightforward. So we're going to learn f of x comma u from data, and then if we're in a continuous setting, maybe we're going to backpropagate through it. Maybe we're going to do something like iterative LQR. So here is sort of the version 0.5, the really simple version of model-based RL. Let's have some base policy, maybe just a random policy. Let's run it in our environment, and let's collect a data set of these tuples x, u, and x prime. So we're walking around randomly using our base policy pi0. We're observing a state, we're observing an action, we're observing the next state, and we're collecting these into our data set. Then step 2, let's use this data set to learn the dynamics model to basically minimize some, let's say, least squares error. Or if you have a probabilistic model, maybe you're going to do maximum likelihood. So let's actually perform this regression and find f of x comma u. And we can represent f of x comma u however we want. Maybe we represent it with a big neural network. We'll see some other choices later on in the lecture. OK, so we can, step 2, we learn our dynamics model. Step 3, backpropagate through that dynamics model to choose your actions, for example, by using iterative LQR from last week. And then step 4 is basically run those actions. OK, so does this work? Well, yes, actually, oftentimes it does work. So this is essentially how system identification works in classical robotics. So if you hear the term system identification, oftentimes it's basically referring to this thing. Some care should be taken to design a good base policy. This is actually in some ways a very trivial statement. If your base policy just takes an action of 0 all the time, if it just sort of sits there, then you're probably not going to see a lot of interesting states. Yes?
What was x prime in the previous slide?
The next state. So you're at state x, you take action u, and you observe a transition to state x prime. Yeah. So for the next time step, x prime becomes the x.
Oh, okay.
Yeah. All right, so some care should be taken to design a good base policy, because you can come up with really, really bad base policies trivially. So if you want to get a good model, you need to make sure your base policy sort of explores the space a little bit. And this is really somewhat domain dependent, so sometimes random actions would work well, sometimes not. But there's some choice to be made there. This kind of approach can be particularly effective if we can hand engineer dynamics representation using our knowledge of physics. So, for example, if we're controlling a robot with 3 links and we know that it's a robot with 3 links, but we just don't know how long or how heavy those links are, we can actually design a model with a fairly small number of free parameters, the lengths of the links and the masses of the links, for example, and try to fit just those parameters to the data. And that actually tends to work pretty well. If we constrain our model class enough, we might actually get exactly the right values of those parameters, assuming that the model actually satisfies is a good model for the real world. So this is kind of the classic system identification approach, but there are a few flaws with this. So in general, actually, the answer is no. And I'm going to give you a little example to illustrate a particular situation where the answer might be no. So this is a mountain with a cliff. And step 1 in our version 0.5 algorithm is to run our base policy and collect data. So let's say your base policy is random. So you have this, you have a little ant on the side of the cliff, and it's just going to do this random walk. And the goal of this ant is to get to the highest point on the mountain. So it's going to be fitting a model that says, if I'm in a particular state and I take a particular action, what's the next state? Basically, what is its xy position and what is its height? So that's the base policy, pi 0. And then step 2 is to learn a dynamics model using this data. So our ant will probably figure out that as it goes further to the right, it tends to get higher and higher on the mountain. So that's a very reasonable thing to conclude from this data, because from this random walk that you saw, the further right it gets, generally the higher it is. So that's good. So now the ant is going to use this really nice model to say, okay, let's backpropagate through it, compute our sequence of actions using iterative LQR, and it's going to do this. So something went wrong here, and in fact it's something that we've seen before. Does anybody have any thoughts about kind of a technical explanation for what's going on here?
The data set is fixed.
The data set is fixed, yes. And this is related to something we saw last week.
It's like Dagger, you don't have some rare things.
Right, so this is just like the situation that we saw on Monday last week with Dagger, where there's a distribution mismatch problem. So the problem is that when we run that base policy, we observe states from p pi 0 of x. So that's the state distribution of our base policy. And when we then use that data to train a model and then optimize for a sequence of actions under that model, and then we run those actions, we get states from a different distribution. Let's call it p pi f of x, where pi f is the policy we get using the dynamics f. So the states that we observe sort of at test time after we take these actions are different from the states that were used to train our dynamics model. So in general, we can't really say that this will work well because of the distribution mismatch. And of course, in this case, the falling off a cliff situation is sort of the pathological case, because once you fall off that cliff, basically the support of these two distributions they don't have the same support. So the p pi f observes these states that are off the end of the cliff, but p pi 0 does not. So there's no way that using states from p pi 0 you could possibly get a dynamics model that is good for the states that you get from p pi f. So this is the distribution mismatch problem, that these two state distributions are not the same. So in general, you cannot guarantee that your dynamics model will be good. The distribution mismatch problem becomes more exacerbated as we use more and more expressive model classes. So that's why on the last slide I mentioned that for this version 0.5 algorithm, it's often used for system identification in kind of more classical robotics domains, but in those cases, the model class is usually fairly constrained. It's something like, you write down the equations of motion, you write down the physics equations for your robot, and then you're just fitting a relatively small number of unknowns. So in that case, your model class is restricted, and you usually assume that that for some setting of those values, the model is a very good model of the real world, and you just have to fit those values. But if your model is very expressive, there are many other possible ways it could explain the data you observe from p pi 0, and many of those ways will not be an accurate reflection of the data from p pi f. All right, so can we do better? So there was an earlier comment about the connection to Dagger. In fact, it's pretty much exactly what we're going to do. So just like with Dagger, we had this question: can we make two state distributions be equal? So that's going to lead us to model-based reinforcement learning version 1.0, where we're going to run the base policy to collect our initial data set. We're going to learn the dynamics. We're going to backpropagate through the dynamics to get our actions. Then we're going to execute those actions. And as we execute those actions, just like with Dagger, all the states, actions, and next state tuples that we visit, we're going to add them to our data set. So in Dagger, we're learning to go from x to u. Now we're learning to go from x comma u to x prime. But same deal, we just want to collect data from the state action distribution under our current dynamics. And then we just repeat this process. And again, like in Dagger, once you repeat it enough times, eventually your data set is populated largely by tuples from your latest policy. So we're going to collect data from p-pi-f, and that's going to solve our distribution mismatch problem. OK, does anybody have any questions about the kind of model-based RL version 1.0? OK. All right, so now that's a nice way to get a good, accurate model of your dynamics, and we can show that the model will be good in the states that we actually visit. But what if we make some mistake? You know, some mistakes that we can make are really bad mistakes. Like if we fall off a cliff, we're in a lot of trouble, and once we're off that cliff, there's really nothing we can do to fix it. But not all mistakes are that bad. So let's say that we're learning a dynamics model for our little car here, and our dynamics model is just a little bit off, so that we think that in order to drive straight, maybe we need to turn the steering wheel 1 degree to the left instead of keeping it perfectly straight. So we're just a little tiny bit off. So we backpropagate through our dynamics. We get a sequence of actions, maybe a long sequence of actions. Maybe we need to drive this car around a racetrack, so our sequence of actions is maybe 30 minutes long. And then we begin executing those actions, and they're all just a tiny bit off. So generally, we've got the right idea. Our model is pretty much good enough to do this task. But because we're a tiny bit off every single time step, those errors are going to accumulate. And even though our entire sequence might be a 30-minute drive around this racetrack, within just a few seconds, we'll drive off the side of the road. So this is this seems like it ought to be a fixable mistake, right? Once you make a little mistake, you can still fix yourself, and your model is probably good enough to allow you to do that. It won't be perfectly optimal, but it will at least allow you to complete that circuit and acquire good data. So we can actually do a little bit better. So because once the car starts veering off course a little bit, even if the model is not perfect, it should be, if it's a decent model, it should be good enough to at least tell you, if you're sufficiently off course, you should correct in the opposite direction. Maybe it won't tell you exactly how much to correct, but at least it'll have that idea. So we can do better with model-based reinforcement learning version 1.5. Actually, pretty much the way you might expect. This is similar to something we saw last Wednesday, which is to use replanning or model predictive control. So we're going to run our base policy just like before, collect our initial data set, fit our initial dynamics, backpropagate through f of xu to choose a sequence of actions, and then we'll just execute the first planned action, observe the resulting state x prime, append it, of course, to the data set, and then replan. So this is what we saw last Wednesday with, if you remember the video with the funny humanoid trying to get up, this is model predictive control, meaning every time step you replan your actions and you only execute the first one. And that way, if the next state that you get from executing that action is not exactly the state you expected, you will actually replan, you'll compensate for that drift. So, and then there's sort of an outer loop where once you've done this enough, then you actually learn your dynamics model. And depending on how you implement this, you could have a really cool multi-threaded implementation where everything is running in parallel and you're training your model as you go, or you can just have an episodic formulation where you run MPC for a certain number of episodes and then just update your model here in step 2. So this is kind of a double loop type of implementation. So the short version here is that basically replanning helps with model errors. So if you're doing model-based RL, doing this kind of replanning every time step or model predictive control goes with that very well, because model predictive control tends to compensate for model errors, because if you don't get exactly the state you expect, that's okay, you just replan for the optimal action. So this is version 1.5. Does anybody have any questions about this method? Yes?
So you retrain the model every new data point you get?
No, so you replan your actions every data point you get. And you can retrain your model every single time step, but you don't have to. So this is why it says every n steps.
Is that backpropagation step expensive? Or
well, so this is, for example, iterative LQR or Monte Carlo tree search. So the answer is, yeah, it's expensive. Usually, well, I mean, it depends a lot on your system, but oftentimes you can do it within a real-time loop. Oftentimes the sacrifices that you make are that you might use a shorter horizon. And this was the case actually in the videos last week with the humanoid. They had a little caption up on the screen that said something like, this is running at 1/7 real time. And that was maybe 3-4 years ago. So since then, they've got it to 1x real time, mainly by shortening the horizon and having a more well-shaped cost function. Because if you have a shorter horizon, you need a cost function that's a little more detailed because you're not planning as far into the future. All right, so that's version 1.5. But that was a very good question about whether or not this is expensive, because in some cases, it is really expensive, and it's a lot of work. And if you're, flying a little low-cost quadrotor, maybe you have to put a bigger, computer on it. Maybe that's expensive. Maybe that adds weight, adds power. You have to implement your code in low-level C rather than in Python. So there's a lot of additional challenges with running MPC. And if you remember this paper from last Monday, where we had the Monte Carlo tree search for playing Atari games, for them this was actually a big part of their motivation. They said that, well, Monte Carlo tree search is great because it can get us really effective policies for playing Atari, but it's super expensive. So let's train a big convnet to try to actually run these games in real time, and we'll use Monte Carlo tree search in their case as a teacher. So depending on what you're doing for step 3 there, for this planning step, hopefully it's cheap enough if you use a small enough horizon, but maybe in some cases it isn't, or maybe in some cases, you can just about run it in real time, but you'd rather use those compute cycles for something else. So what if we directly try to train a policy instead of having to replan every step? So we can kind of draw a little computation graph that shows all the pieces of this dynamical system. We have our cost function, we have our dynamics over here, and then we have the policy. So this is not a probabilistic graphical model, this is just a computation graph. So this is saying that your policy is going to choose some action. Together the state and action are going to determine the cost, and together the state and action are going to go into the dynamics, which is going to determine the next state, and so on. So if we're learning a model, we're going to, f of x, that's the thing we're learning. Pi theta of x is our policy. So in principle, if we have representations of both of these objects, both the f and the pi, we should be able to backpropagate through this whole thing. And I'm intentionally using completely deterministic notation for everything. If we have stochastic dynamics or stochastic policies, you could do this also, but it takes a little bit more work to derive the math for it. So let's just deal with the deterministic case for now. So if we have both f and pi, we could just backprop through all of them, and we could just write down an optimization problem that says minimize the cost at all time steps subject to the parameters of the policy. So easy for deterministic policies. For stochastic policies, we'll discuss this later. So this is kind of model-based reinforcement learning version 2.0, where we run our base policy, collect our data set of transitions, learn our dynamics by, let's say, minimizing squared error or something like that. Then we backpropagate through the dynamics into the policy to optimize pi theta. So this is, you can kind of think of this as a gigantic recurrent network. And then we run pi theta and then append the visited states to our data set and then repeat in order to compensate for the distribution mismatch problem. So this is kind of a classic model-based policy search algorithm. Does this make sense to everybody? Does anybody have any questions about this procedure? Yes?
So you go like t steps in the future then backpropagate, or are you just doing one at a time in this case?
Right. So the question is, do you go t steps into the future, or do you go one step at a time? So in order to minimize the cost over an entire episode length, you do have to go for multiple steps. And that's actually a big part of the reason why this procedure sometimes is very difficult to apply. So you would basically take this graph. I only drew 2 time steps here, but you would unroll it for however many steps you have in your episode. So if you're driving the car around the racetrack, if it's like a 30-minute race, then you would unroll it for the whole 30 minutes and backpropagate all the way through that chain. Yes?
So what's the advantage of this method over 1.5 where you're replanning?
So the main advantage of this method over 1.5 is that in step 4, you just run your policy. So the policy dynamically selects an action in response to the current state. So that means that it's going to compensate for mistakes, to the best of its ability, and you don't necessarily need to replan every time step. Presumably, it's not going to be quite as good as replanning every time step, but it potentially is a lot cheaper. Okay. So here's a summary of these model-based RL algorithms that I presented. So we had version 0.5, which is collect random samples, train your dynamics, and then plan, and then just execute that plan. So the advantage of that is that it's simple. There's no kind of iterative procedure. You could, in principle, use data that somebody else just gave you, so you don't have to actively collect more data. The disadvantage of this is that in the general case it might not work because of the distribution mismatch problem. Yes?
Does that assume the policy is like continuous, so you can actually like take derivatives?
So it assumes that the action is a continuous function of the state. Now, if you have discrete actions, what you would probably want to do is you'd want to output a distribution of our actions. So, for example, you might have a softmax. There's still some tricks you can use to backpropagate through that. Actually, backpropagating through multinomials like that is an active area of research right now in deep learning, but there are tricks you can use to do that. With continuous actions, you can basically, the short version of how you can make it stochastic is you can use what's called the reparameterization trick. So you can say it's like a Gaussian, and then if you have
Question?
Yes.
So why don't we learn the dynamics and the policy jointly?
Why don't we learn the dynamics and policy jointly? So the reason for that is that when you learn the dynamics, you're trying to actually figure out what nature does. When you learn the policy, you're trying to figure out how to minimize the cost. So if you learn the dynamics that minimizes the cost, that's like saying, I'm going to sit down and imagine how I'd like the world to work so that I get the most money. So if I'm going to sit down and imagine how I'd like the world to work so I can get the most money, I'm going to imagine, well, people just give me bags of money. But that's, of course, not what actually happens in the real world. So the dynamics has to match the real world, but the policy has to just do well. All right, so the disadvantage of this version 0.5 is the distribution mismatch problem, but it's probably worth saying here that this is not an unreasonable thing to do in some cases. For example, if you have let's say you know the physics of your robot and you just don't know the masses or the lengths of some of the links, well, that's actually like a pretty reasonable thing to do, because if your model is constrained enough and you just have to figure out a few free parameters and you design your base policy carefully, that's quite a reasonable way to go. But for very expressive models, especially big neural network models, version 0.5 will generally suffer from the distribution mismatch problem, and you will not get good results. So that leads us to version 1.0, which is sort of the first example of a standard, reasonably effective model-based RL method, which is that you iteratively collect your data, replan, and then collect more data. The advantage of this is that it's simple and it solves the distribution mismatch problem. The disadvantage is that the open loop plan, so open loop means that you plan your actions and then you just execute them blindly without correction. The open loop plan might perform poorly, especially in stochastic domains, where you can't perfectly predict your state. You can only predict it up to a distribution. So I should say, by the way, that version 1.0, under some assumptions, like, for example, deterministic dynamics, is a perfectly viable way to solve the model-based RL problem. It just might not be the best one. In stochastic domains, it gets a little more dicey. So that leads us to version 1.5, which is you iteratively collect data and then use MPC, meaning that you replan at every step. The advantage of this is that it's robust to small model errors. So even if your model is not quite perfect, so long as it has the right idea, you'll probably get pretty good data, and then you can fine-tune your model. The disadvantage is that it's computationally quite expensive, and you need to have some planning algorithm available to actually perform this iterative replanning. So in some domains that's straightforward. In some domains you might need to work a little bit to design your planning algorithm. So then we have version 2.0, which is backpropagate directly into the policy. And this is a model-based policy search algorithm. There's no planning going on and no LQG or anything like that. You're just directly optimizing your policy. So it's computationally cheap at runtime because you just execute your policy, which might be, let's say, a feed-forward network or something. But it can be numerically quite unstable, especially in stochastic domains. And I'll get more into this later. In fact, actually, a lot of the Wednesday lecture is going to be dealing with this problem. So I'll describe this problem more later on. But before I do that, let's talk about an example of model-based RL in action. So this is an example, actually, of algorithm version 2.0. And it's not using neural nets. It's actually just using Gaussian processes for everything. So this is a paper from Mark Desenroth from when he was a postdoc at University of Washington. And the goal in this paper is to control this low-cost robotic arm. So here's the algorithm that they're going to be proposing. It's very, very much like the version 2.0 algorithm. You're going to run some initial policy to collect a data set. Then we're going to learn a Gaussian process model. So we're going to fit a Gaussian process to these things. And the Gaussian process is going to give us the conditional distribution of x prime conditioned on x and u. So in the Gaussian process, you have your inputs and your outputs. So the x comma u is the input, and the x prime is the output. Then you can actually backpropagate through this Gaussian process. So it's a stochastic dynamics model, and optimize the expectation of the cost under a stochastic policy pi u given x. and they represent the policy with a RBF network. There are some conditions that they have under the on the class of policies that can represent. RBF network is a pretty simple class. And then you run your policy, collect additional data, append that data to your data set, and the usual story you repeat, and so on. So this is the algorithm that they're going to use. It's very much like this version 2.0 model-based RL algorithm. And the main trick in this method is the step 3, backpropagating through your Gaussian process dynamics into the policy to compute pi theta u given x. So the problem with this step is that if everything is stochastic, if the Gaussian process is stochastic model of the dynamics, the policy is a stochastic distribution over actions. The challenge is that you need to compute these state marginals because you need to minimize the cost, the expectation of the cost under those state distributions. So if p of x is Gaussian, it turns out that you can get the distribution over the next state in closed form using your Gaussian process. Because the Gaussian process, the particular non-parametric structure is basically, at a very high level, you can think of it as giving you a different Gaussian for every single data point. So if you're starting with a Gaussian, you're going to get some non-Gaussian but analytic distribution over the next state. So what they're going to do is they're going to run this Gaussian process forward at each state from a Gaussian distribution, and then they're going to project this non-Gaussian xt plus 1 down to a Gaussian approximation using moment matching. So the procedure for essentially forward propagation here is take your current Gaussian state distribution, run the GP forward, get a non-Gaussian distribution, project it down to a Gaussian, so that's what they're illustrating here, and then do this whole thing again. And that'll get them a Gaussian distribution over states at every time step for the current policy. So then if they have a Gaussian distribution over states at every time step, assuming C has some nice form like a quadratic, computing the expectation of C under X can be done analytically. And then you just have the sequence of equations for computing the expectation of the cost at every time step. And then you just have to differentiate that whole thing going all the way back to the beginning. And then you get your derivatives of your policy parameters. So it's kind of a hairy procedure, and the derivatives in this thing are actually quite nasty. But so long as you can compute those derivatives, you're in good shape, and you can optimize your policy. Yes?
When you say that the p of x t plus 1 is non-Gaussian,
Mm-hmm.
how are you actually getting that distribution? Is that from data, or?
No. So this is, there's no data at this point. So this is just step 3. So you've already trained your dynamics model. Your dynamics model is a Gaussian process. And this p bar xt plus 1, this is just what you get if you take a Gaussian process that gives you p of x prime given xu. You have your u given x here. And then you just need to multiply all those together and integrate out x and u to get the next state distribution. And the equations for that are in the paper. They're a little bit too lengthy to go into here. But the short versions that you get, you end up with an analytic distribution that you can actually represent. It's just not Gaussian. So this is what this picture is showing. You have some funny peaky thing, and then they're going to just project it down to a single Gaussian at every step. OK, so this is kind of nice. It's it's using Gaussian processes, although in principle you could probably extend this to use neural nets for p of x prime given xu as well. And use the same kind of projection trick. And as I mentioned before, they're using this to control a low-cost robotic arm. So it's kind of a nice video that we can watch here. They're actually learning vision-based control, although the vision is a little bit there's a little bit of engineering there. So they just use a blob detector to figure out the position of that little cube that the arm is holding, and the input to the GP is just the position of the cube in the camera frame. So it's just a 2D position. And then they're using the position of that cube and the actions at the joints of the arm to figure out the dynamics. So it's actually quite a nice dynamics model just from the position of the cube and the actions at the arm to the next position of the cube. And then they're using that to get this arm to stack these blocks. So this is just showing the final policy once it's been trained. And the input is just coming from this camera. So the robot arm, as far as I understand, doesn't actually have joint encoders. OK. So that's kind of neat. Now this might make us kind of ask the following question: what kind of models should we use to fit our dynamics? Well, in this paper, they use Gaussian processes. We also know that we could use neural nets. We could use other stuff. So how do we choose the type of model that we should be using for model-based RL? So all these different classes of models have certain strengths and certain weaknesses. So let's start with the Gaussian processes, and then I'll talk about neural nets and also a few other options. So with the Gaussian processes, as I said before, the idea is that you just fit a GP where the input is your tuple of state and action, and the output is the next state. It's very data efficient. So GPs in general are very data efficient models, meaning that they'll give you sort of sensible dynamics even with a relatively small amount of data, which is great for model-based RL, because in model-based RL, you'd like to learn quickly. You'd like to learn from a small amount of data. But they tend to not be so great with non-smooth dynamics. In fact, the method in the case study previously actually assumes not only that you're using a GP, but that you're using a GP with a squared exponential kernel. And the squared exponential kernel corresponds to a prior on smooth functions. So GPs tend to be not so great with non-smooth dynamics of the type that you might get, for example, if you have a physical system with contact. So if you have a robot that touches something, that's in general a non-smooth phenomenon. And there are many other cases where you have non-smooth phenomena. GPs tend to get pretty slow when the data set is big. So in general, if you're going to optimize the parameters of your GP, that's going to scale cubically with the number of data points that you have. There are ways to improve that, but in general, they tend to be quite cumbersome when your data set is large. With neural nets, what we would do, it's pretty much the straightforward regression thing. So the input to the neural net would be a tuple of state and action. The output is the next state. This picture, by the way, is from a paper on fitting neural net models for helicopter dynamics. And this is just illustrating the hyperplane cuts that you get from rectified linear units. So the input is a tuple of state and action. The output is the next state. If you use, let's say, a kind of a least squares loss, a Euclidean distance training loss, this corresponds to actually to a Gaussian distribution over the next state, right? Because the log of a Gaussian is a quadratic. So if your loss is quadratic, what you're really doing is you're doing maximum likelihood learning for a Gaussian model. You can use more complex losses. So you could, for example, output the parameters of a Gaussian mixture. And I'll show an example in the next slide of a paper that actually does that. If you have discrete states and actions, you might output, let's say, a softmax over the next state. The big advantage of neural networks is that they are very expressive and they scale well with the size of the data set, so you could fit them to large amounts of training data. But their big disadvantage, especially when it comes to model-based RL, is that they tend to not be so great in low data regimes. You can use a much smaller network, which will do better in the low data regime, but then you lose the advantage up here. So you kind of have to choose the size of your model, and unlike a GP, since it's not a Bayesian model, it's not going to naturally adapt to the size of your data set. So part of the reason why neural networks are actually not used as much in model-based RL is because of this disadvantage down here. Because the low data regime is exactly when you need your model to be decent, because you'd like to be data efficient when you're doing model-based RL. But we'll talk later on in the course about situations where you actually don't have any choice, where you have to use big expressive models like neural nets. This comes up, for example, if you're predicting images. But before I say a few words about that, let me talk about some other options. So there are a few other options for fitting dynamics models that are also worth knowing about. For example, one method of fitting dynamics that tends to work surprisingly well is a Gaussian mixture model. So you can fit a Gaussian mixture model to tuples x, u, and x prime. So you literally just construct a set of vectors x, u, and x prime, just concatenate them all together, and fit a big Gaussian mixture model to them. And that's what's being shown here. This is actually a Gaussian mixture model for a pendulum swing-up task. You can train your Gaussian mixture model on these tuples, and then when you need to use that model, you actually condition on x and u to get a distribution over x prime. So in such a Gaussian mixture model, for the ith mixture element, the p of x comma u of that element basically tells you the region in which this mode is active. And when you condition a Gaussian, what you get is actually a linear Gaussian. So the next state becomes a linear function of the current state in action. So you can think of this Gaussian mixture model as actually decomposing the space into a set of linear modes where p of x comma u tells you the region in which that mode is active, and p of x prime given x comma u tells you which mode it is, which is actually quite nice. So if you believe, for example, that a piecewise linear model is sort of a good model of your system, then a Gaussian mixture model can in principle give you a good decomposition of the space into a bunch of linear modes, with the caveat that if your space is very high dimensional, this is going to be potentially kind of awful. But it can work reasonably well in some cases. There are other classes of models that can work pretty well. For example, domain-specific models. If you know something about your system, if you can write down, for example, the equations of physics, as in that system identification case that I described for version 0.5, that's also a good idea sometimes. And then later on in the course, I think this will actually be a lecture that Chelsea will do in like week 4 or 5, we'll talk about situations where neural network models are kind of our only option if we have to deal with really, really high bandwidth observations like videos. So if you want, for example, to build a dynamics model where you're predicting the next image, then you might need a really high capacity model like a neural net, and we'll have more on this later on in the course. Does anybody have any questions about different options? Yes?
So the neural network model, when you say that it's not so great in low data regimes, what if you restrict the number of parameters in your neural network?
Yep, so that's a good question. What if you restrict the number of parameters in the neural net in the low data regime? So this is, yeah, this last point is a little bit kind of circumstantial, right? So you can restrict the number of parameters, and then you'll be good in the low data regime, but you'll be bad in the high data regime. So you have to kind of choose one or the other. The nice thing about GPs is that they will sort of naturally adapt to the size of your data set because they are a Bayesian model. So with neural nets, you could do that, but then you sort of lose the big benefit here. All right, so these are the different choices that we can have for global models. And let me actually give you an example of a method that uses this thing, the neural net that outputs a Gaussian mixture model parameters. We actually already saw an example of a neural net that outputs Gaussian mixture model parameters last Monday when we talked about imitation learning, but that was a mixture model for predicting actions conditioned on states. Now we'll actually see a mixture model for predicting the next state. So this is a paper that's not actually doing control. What they're doing here is they're doing prediction of human poses. So what they want to do is they want to observe a sequence of poses taken from motion capture of a person, and then they want to predict future poses. And the way that they're doing this is that they have a little feed-forward. This is the encoder recurrent decoder model. They have a little feed-forward component that processes the current state. Then they have a little recurrent component that predicts the future, and then they decode it using another little feed-forward component that decodes into the next state. So it's a recurrent neural network model that's going to have a little encoder to process the current state, predict the next one, and so on. And if they want to perform a rollout for many steps, what they'll do is they'll actually decode the current state of let's say the human, and then they feed it as input at the next time step to re-encode it into the next time step. So here's sort of that picture blown up a little bit. And the place where the Gaussian mixture model is going to come in is right up here. So this little feed-forward component is going to output actually the parameters of a Gaussian mixture with some pre-selected number of elements. In this case, I believe it's 5 elements. So that means they output 5 means and 5 covariances. And then there's just a sampling operation that samples from this thing up here, gives you an individual pose, and then that pose is fed at the next time step. So the sampling operation is in general non-differentiable, and it's just fed in as input at the next step. There is another component to this paper which actually uses this for tracking body parts in videos, but I'm not going to talk about that too much. Okay. Now, one of the things that I'm going to show you from this paper is actually a comparison of different prediction models. So there's the model that's proposed in this paper, which is this recurrent encoder recurrent decoder model. But there are other models that people have proposed in the literature, and there's a nice video that compares them. So one of the ones that you're going to see is what's called a conditional restricted Boltzmann machine, which is a stochastic neural network model with binary hidden units. So this was proposed by Taylor et al. There's going to be an example of actually a Gaussian process latent variable model, which is a fancy version of a Gaussian process that you'll see as well. There are linear and switching linear dynamical systems. I don't think there's an example of this in the video, but I just wanted to mention this because this is also a popular class of dynamics models. So it's basically a linear model, but that can switch into different linear modes. And then there are lots of others. So we're going to compare the encoder recurrent decoder. We're going to compare a standard LSTM model. So this is the one that doesn't have the encoder and decoder components. It's just a stacked LSTM, which is a recurrent neural network. The conditional RBM. And then there's going to be a simple n-gram baseline that just takes the neighborhood and tries to predict the pose from that. And then the Gaussian process. So here, I'm about to play this video, but basically what you'll see is on the left, you'll see the ground truth. So this is motion capture of an actual person, in this case walking. You'll see the encoder recurrent decoder here in the second column. You'll see the LSTM, the conditional RBM. This is sort of the n-gram baseline, and this is the Gaussian process. And in this case, they're trained on the same data. And when the character is green, that's the observation. So that's just all ground truth data that's being used to condition the model. And blue will be the predictions. So when it switches to blue, those are the predictions from each of the models. And we can play them and see what happens. So now all of the models are predicting, and you can see some of them do better than others, and some of them make kind of interesting mistakes. So for example, the LSTM kind of tends to just get stuck in a particular pose. Some of them, this one I suspect is actually, it's just a very difficult model to train. So if those of you that are familiar with restricted Boltzmann machines might know that actually training RBMs tends to be a little bit of an art. But yeah, you can see that they're all making some kind of prediction, some of them more sensible than others. And they all have kind of, when they fail, they all have slightly different failure modes. GPs, when they fail, they tend to just sort of saturate into the mean pose and just get stuck there. The neural network models, they tend to extrapolate sometimes in slightly crazy ways. So you particularly see the crazy extrapolation in CRBM. A little bit, yeah. So this is using a publicly available motion capture data set, and those of you that are interested in playing around with predictive models, this is the CMU motion capture database. You're welcome to grab that and give that a shot. All right, does anyone have any questions about any of this stuff? Okay, so let's talk about now some of the problems with global models. So when I say global model, what I mean is you want to basically fit some function to f of x comma u, and you want that function to basically be correct everywhere, so that when you backpropagate through it, when you plan through it, you get good plans regardless of where you might be in the state space. So that's a global model. And that's basically what we've used so far in all of the model-based RL methods that we've described. The problem with these global models is that if you have a very good planner, it'll basically do the worst possible thing. It'll basically seek out the regions where the model is erroneously optimistic. Like that example with the ant walking on the cliff, right? If your model is making some mistake, if it's sort of predicting something that's better than it really is, the model-based RL algorithm will choose to go there. And sometimes this is a good thing. It's sort of hard negative mining. It goes to the places where you can improve your model the most. But sometimes there's just so many of these places that you could go in really high dimensional spaces that your model is essentially trying to plug all the holes, all the places where your planner can escape to go into erroneously optimistic regions, and there's just too many holes to plug, and you'll just end up visiting all these different places and making basically all the possible mistakes until you get it right. So sometimes maybe you don't want to have to make every possible mistake before you get the right behavior. Maybe you can do better than this. So so the trouble with the global models is that you need to typically find very good models in most of the state space before you converge to a good solution, especially in problems where the model tends to be overly optimistic and where there's sort of one good thing that you'd like to find, and it's kind of hard to find, and there are many ways to get it wrong. So in some tasks, basically the reason that this kind of happens is that in some tasks the model is actually much more complex than the optimal behavior. And I can give you a very simple example of this. Let's say that you're trying to pick up a little cup, like a coffee mug or something, right? The actual physical act of picking up that mug is not that complicated. The mug is sort of made for your hand. That's why we made the mug. So you just have to kind of curl your fingers around, insert it into the handle, and pick it up. So physically, it's a fairly simple act. The dynamics of that system are fiendishly complex, right? So there's really complicated contact dynamics between the mug and your fingers. Your fingers have really complicated muscles and tendons and so on. Maybe if the mug is made of plastic, maybe it's going to bend. So if you try to model the physics of this thing in very high detail, that might actually be exceptionally hard. Probably substantially harder than actually performing this task. So one of the things we can do to deal with these issues, to deal with situations where the true global model is more complex than the policy, to deal with situations where there are many more ways to get the wrong answer than the right answer, is that instead of trying to fit a global model that's good everywhere, to try to just fit a local model that's good in the region where you're currently located. So a little bit of kind of more nitty-gritty mathematical motivation for this. We started off this discussion of model-based RL by saying that, well, if you want to backpropagate through your dynamics, if you want to solve the optimal control problem, you need these derivatives down here. The derivatives of the dynamics are the ones that we don't know, so we're going to fit some big global model, differentiate that model, and get those derivatives. But if all you really want is those derivatives, well, why not just fit the derivatives directly? So why not just take the current trajectories that you're executing, try to figure out what the derivatives of the dynamics around those trajectories are, and just plug those into your optimal control algorithm, plug those into LQR, for example. And we can do that, and that allows us to use local models. So we're just going to fit the derivatives around the current trajectory or policy. So that means that if these are your trajectories, you started over here, you ran it a bunch of times, maybe your environment is a little stochastic, so they're not exactly the same, but they all kind of go into similar regions. We just want to fit a line that at every time step that tells us how will the next state depend on the current state in action. And it's a line because we just want to approximate these derivatives, or hyperplane in general. So yeah, and we need them at every time step. So if we have many time steps, we fit a different one at every time step. So let's say that we have a very simple controller. We have a controller that at every time step gives us a linear Gaussian distribution over actions. So from LQR last week, we saw that we get a linear controller. Today, we're going to talk about how we can actually get a linear Gaussian controller, which is basically a linear controller with a little bit of noise added in. So I'll talk about this more in subsequent slides. But if we have this kind of controller, just a different linear policy at every time step, we can execute it on the robot, get a bunch of trajectories, and then we can just fit the dynamics. So we execute our controller on the robot, we get a data set of trajectories. Those trajectories consist of states and actions. At every time step, we're going to fit a different, very simple linear dynamics model. I'll get more into this in a second. And that linear dynamical model, the dynamics model gives us maybe conditionally Gaussian dynamics. So it's some linear mean and some covariance. So we're approximating f of xt comma ut by a linear system, different at every time step, which is an approximation of the derivatives of the real dynamical system, which we can then feed into some trajectory improvement procedure like LQR from last week, and then we can repeat this process. So this is kind of a high-level outline of one of these local model-based methods. Run your current guess at your policy or your trajectory distribution, collect some trajectories, fit local models at every time step, which correspond to these derivatives of your dynamics, use them to improve your behavior, and then repeat. That's the idea at a high level. So you throw out your model every single iteration, fit a new one, and we're not going to be using a really expressive model. There's no deep learning here yet. There will be on Wednesday. For now, it's just very simple linear models. OK, so let's dig into the pieces of this method a little bit more. First, I'm going to talk about what control you're going to execute, and then I'm going to talk about how you actually might fit the dynamics. So which controller should we execute? Well, what if we're using iterative LQR to plan our trajectory? Iterative LQR gives us the following things. It gives us the x hat and u hat, so that's the actual trajectory that we've planned. U's are the actions, x's are the states. And it also gives us these feedback controller parameters. So if you remember from the lecture last Wednesday, in iterative LQR, the actions that you actually execute are some feedback matrix times the difference in the states, plus an open loop term, plus the reference action. So this is what iterative LQR gives you. So what can we execute? Well, version 0.5, what if we just say that our distribution over actions is just a delta function at the planned action? So basically, with probability 1, take the action that you planned, and everything else is probability 0. So that just means execute the actions you've planned in open loop. OK, so that's kind of a reasonable thing. That's a little bit like the model-based RL algorithm version 1.0. So as we saw with the model-based RL version 1.0, it's a reasonable option, but it doesn't correct for deviations or drift. So if your model is not quite perfect, the errors are going to accumulate and you're going to drift off the road, just like we did with that little car example. And it's particularly problematic for these local models because the local models are pretty weak. So they're often going to get the right idea, but they're very rarely going to be perfect. So this is often not such a great plan because of the drift. So version 1.0, which is substantially better, is to actually just execute this linear feedback controller. So again, it's a delta function. It says with probability 1, take the action given by the feedback controller from LQR, and everything else is probability 0. That's a much better option because now you can correct for drift. But there is a little bit of a problem with this, which is kind of subtle. Does anybody have any idea what that problem might be? Any guesses?
It's designed around the linearization of the dynamics that you got earlier.
Yes? So, right, so it's designed around the linearization that you got earlier, which might be wrong. I'll get into how to deal with that in a later slide, but that is definitely one problem with this. So our purpose of running this controller is to generate data that we're then going to fit, that we're going to then use to fit a local model of the dynamics. this is a deterministic policy, meaning that it takes the same action every single time. In order to fit a linearization of the dynamics, you need more than one sample. So if you run exactly the same policy every single time, if your real physical system is not stochastic, if it's fairly deterministic, maybe it has a little bit of noise but not too much, the problem is that this is going to be basically too good. So you run this multiple times, and in the extreme case, you just basically get the same exact trajectory each time. And if you saw exactly the same trajectory each time, there's just not enough variability for you to fit any meaningful linearization. Because you observe literally the same numerical values, you try to do some kind of linear regression on that, and it tells you that you have a singular matrix that you're trying to invert. So it's a little bit too good. It sort of gives you, it'll not give you this nice kind of variability of trajectories. It'll just give you one trajectory over and over again. So you can actually do quite a bit better than this with version 2.0, where we design actually a controller that is almost like this feedback controller here, but is a little bit stochastic. And by being a little bit stochastic, it'll sort of give us trajectories that are all kind of similar, but a little bit different. Just different enough that they'll show us essentially how does the next state actually vary as we change the preceding state in action. So the question with this version 2.0 method is, how do we choose the variance? How do we choose how much noise to inject? So we could just choose it manually. We could just choose some constant, maybe identity times some constant. But there's actually a pretty simple and much better way to do it, which I'll sort of describe a little bit informally here, but there's a paper that describes it in more detail, which is that you set the covariance to be the inverse of the action portion of the Q function matrix. So if you remember from the iterative LQR lecture, we computed this Q function, which is the cost to go at every time step. So this was the equation from the LQR lecture, where we said the cost, if you're in this state and take this action, for the rest of time is going to be given by this quadratic equation, where there's a linear component and a quadratic component. And this matrix component Q has a top left portion that depends on state and a bottom right portion that depends on action. So what happens if we set the covariance to be the inverse of the action portion of that matrix? So this QUU is just the bottom right of this matrix Q. So if QU is big, that means that changing U is going to change the Q value a lot, right? Because that's literally what goes in here. So there's big numbers in the bottom right. They're multiplied by U on either side. That means that changing U is going to have a big effect on the Q value. So the intuition behind what this means is that the cost to go, the cost that you'll experience from this time step until the end of time, is going to depend strongly on the action that you take right now. If QU is small, that means that the action you take now has almost no effect on the total cost that you'll experience from now until the end of time. So the intuition behind setting your noise to be the inverse of this QU thing is that if QU is big, that means you use small noise, because your current time step is very important. Choosing the action correctly is very important to your cost to go, so you should not inject lots of noise. You shouldn't play with the action here, because this time point is critical. If QU is small, that means that the action you take now has very little effect on your cost. So it's OK to be really random. It's OK to explore, because it's probably not going to cause you to do anything too adverse. So this is a very reasonable way to do this. Does this make sense to people, or does anybody have any questions about it? OK, good. So that's kind of the intuition behind it. There's actually a mathematical formalism that tells you what exactly we're doing when we set the covariance like this. So standard LQR solves, of course, the minimal cost problem. So it tries to minimize the cost of your trajectory. If you use a linear Gaussian controller of this form with the covariance set to QU inverse, what you're actually doing is you're finding the optimal solution to a slightly different control problem, a control problem where you're minimizing the expected cost minus the entropy. So this is a maximum entropy controller. It's the controller that has the largest entropy while minimizing the cost. And the proof of why this is the case is a little bit more involved, so I won't get into it in this lecture. But we'll use this fact that this kind of linear Gaussian controller actually optimizes a maximum entropy control problem later. And this idea of maximizing entropy is actually also going to come up later on in the course when we talk about model-free RL as well. So the maximum entropy solution, which is to act as randomly as possible while minimizing cost. So basically, as random as you can get without incurring too much of a loss in terms of your cost. All right. So just to summarize this algorithm with local models again, You run your controller P of u given x, which is going to be this linear Gaussian controller, collect your trajectories, fit the dynamics at every time step, fit linear dynamics at every time step. Those are going to be your approximate derivatives. Feed those approximate derivatives into LQR, get an updated trajectory, and then run it again. OK, so now we're almost there. We need to figure out how to actually fit the dynamics. But that part is going to be actually really easy, because when we fit the dynamics, we know that we want linear dynamics. So we have this data set, and we're going to fit P of xt plus 1 given xt ut at every time step using linear regression, using just the data at that time step. So that means that we're really fitting this, again, linear Gaussian distribution, where the things that we want to find out are AT, BT, C, this should be CT, and the noise. The noise doesn't matter, because as I said before, in LQR, when you have Gaussian noise, it's symmetric to that Gaussian noise, so the solution doesn't change. So we're just going to fit these A and B, for example, using just standard linear regression. That's version 1.0. Now, the trouble with linear regression, of course, is that the number of samples that you'll need is going to scale with the dimensionality of your system. So as you have more and more dimensions in your system, you're going to need more and more samples. That's sometimes OK if you have maybe a 10-dimensional system. That's not a big deal. And it's really, really simple, which is nice. But you can probably do a little bit better. And version 2.0 of this is to fit this distribution using Bayesian linear regression. So Bayesian linear regression means that we're going to impose a prior on our linearization. And where can we get that prior? Well, you can get that prior from your favorite global model. So you can basically do all the stuff that we did before, fit a GP, fit a neural net, fit a Gaussian mixture model, fit some parameterized model of physics. It doesn't have to be a great global model, but it can act as a prior on this linear fit. And the nice thing about fitting that global model here is that for the global model, you can use all of your data. You can use all the time steps, all the previous iterations, and so on. Basically do the best you can with a global model, but then you're still going to use this local model for your updates, and the global model is just going to act as a prior. So if there's something at that current time step that strongly disagrees with your global model, the linear fit will override that. But if they're in reasonably good agreement, then the global model will give you a little bit more information in the prior. Yes?
When we're doing this fitting around, so we're doing this fitting around our trajectory, is the input to, I guess, whatever we need to learn the model, are they the samples x and u, or is it x minus the...
Yes, so this is a good question. So when we talked about, just to summarize this, when we talked about LQR, especially iterative LQR, we saw that when we have a nonlinear system, what we do is we first convert into this delta u and delta x. So delta x is x minus x hat, delta u is u minus u hat. So the question is, when we perform this linear fit, are we fitting delta x's and delta u's or x's and u's? And the answer is that actually, it turns out to really not matter, because it's just the x hat and u hat are just a constant. So you can either fit x's and u's and then subtract x hat and u hat, or you can fit the delta x's and delta u's, in which case you just have to convert your global model into that same form, which you can do very easily just by subtracting the x hats and u hats from either side. So in general, it actually makes no difference, but you do have to make sure that you take that into account. So you can either subtract the x hats and u hats after fitting this thing inside the LQR procedure, or you can subtract it beforehand, in which case the main thing you need to do is make sure that if you're using a global model prior, that you compensate for that. They do depend on time. They don't depend so they depend on time and they depend on the iteration, but they don't depend on any kind of observation or anything like that. Yes?
And how is NT determined here?
Well, so when you do least squares, you can figure out the covariance just by taking literally the covariance of the differences between the real data points, the real x primes, and the predicted ones, and that'll get you the optimal NT. But it also, in reality, you actually don't need this because LQR is symmetric to it. So you could also just skip it, and everything will be fine. All right. So now we're almost there with local models. There's just one problem that we have to solve, which is a little bit specific to this method, but I want to go through it anyway because it's going to introduce a few mathematical tools that we'll use again later in the course. So the problem, and this actually relates to a point that someone brought up earlier, which is that our linearization is only valid in a particular region. So we haven't actually solved that problem yet. So basically the problem is that our true dynamics are nonlinear. We're going to use this pretty silly linear fit to approximate the dynamics, which means that far away from our data is going to be totally wrong. And if we feed those linear dynamics to our LQR procedure, it's going to give us a new controller that will maybe actually visit one of these regions where the dynamics are totally wrong. and when we actually run it on our real system, it might do something completely different. And this in general can cause your algorithm to diverge. If you're using it to control some real physical system, maybe a vehicle or a robot, it'll also cause that system to break. So it'll generally be just kind of bad news. So the problem is that the dynamics are only good locally, and there is nothing controlling how big of a step we take when we improve our trajectory. So we'd like to somehow keep the trajectory close to where it was before, so that this error between the fitted linear dynamics and the true nonlinear dynamics is not too huge. So how can we do that? How can we stay close to the old controller? So remember that in this case, our controller is this linear Gaussian thing. And a linear Gaussian controller, or in fact actually any policy, induces a probability distribution over trajectories. So this we saw in an earlier lecture. We saw that the distribution over trajectories is just the product of the initial state, the policy at every time step, and the dynamics at every time step. So we multiply all these together, and we get p of tau. So what we really want to do is we want to keep the new p of tau close to the old p of tau, which I'm going to denote with p bar tau. So if the trajectory distribution is close to the old one, then we can reasonably hope that the dynamics near the new trajectory distribution won't be too different. So how can we keep two distributions close to each other? Well, we need some measure of how close together two distributions are. A very good measure is the KL divergence, and I'll define this on the next slide. So we can use KL divergence, and we can just say, let's optimize a new linear Gaussian controller, but in such a way that the KL divergence between the trajectory distributions of the new controller and the old one is bounded by some step size epsilon. And this is called a trust region. So in this lecture, I'm going to actually derive how we can apply a trust region specifically to linear Gaussian controllers, but we'll actually see much later on in the course when we talk about trust region policy optimization, how you can also impose a trust region on complex neural network policies. So for today, I'll go through the linear Gaussian version, but some of these formulas are going to come up again later on in the course, so it's a good idea to get a good handle on them. So this is what I just said, that this kind of trust region thing is going to be important later. Now let's define the KL divergence. So this is just from the definition of KL divergence. This is the expectation under p of tau of log p of tau minus log p bar of tau. So where p of tau is the one on the left and p bar of tau is the one on the right. P bar is the old one, p tau is the new one. Was there a question?
Yep. We just want to regularize so we don't like spiral out of control. Is that
Yep.
like the intuition?
Yeah, so the intuition is that you want your new controller to generate trajectories that are close to your old samples, because if it goes far away, this linearization that you fitted is not really valid anymore, and you might get some crazy stuff. And in the model-free case, there's a slightly different motivation to it, but it'll basically be kind of similar. There'll be a linearization. You want to stay close to that linearization. And that's going to be much later in the course. So this is the definition of KL divergence. And this is, again, the definition of a trajectory distribution from the last slide. And what we're going to do is we're going to substitute. We're going to take this thing, and we're going to plug it in here. But before we do that, let's look at the definition of p bar tau. P bar tau is almost exactly the same as p tau, because the only thing that changed between the previous controller and the new one is the controller itself, the u given x. The dynamics and the initial state distribution don't change because we don't get to pick those. Those are set by nature. So p bar tau is exactly the same as p tau except for this term. And that's going to be very important for what we're going to do next. So we're going to plug these in. For now, I'll just omit the expectation. I'm just going to write out log p tau minus log p bar tau. And all I did here is the first line, I just substituted this thing and took the log of everything. So when you take the log of a product, it's the sum of logs. So that means that you have log p of x1 plus the sum over the time steps of p of u given x and log p of xt plus 1 given xt ut. And on the bottom is the same thing, but for this, for p bar tau. And now, of course, as you can see here, this term and this term are just going to cancel because they're the same, and one is the negative of the other. The dynamics are going to cancel because here you're adding it and here you're subtracting it. So the only thing that we're left with when we take log p tau minus log p bar tau is the difference of the actual controllers at every time step. And that's what's going to allow us to produce a useful way to impose this constraint. So now this is what we have. We're going to simplify it. And now we just have the expectation under the new trajectory distribution of the sum of the differences between the log probabilities of the controllers. Now, because inside the sum, every time step only depends on ut and xt, we can actually take the sum outside of the expectation. And now we can actually just do the expectation over only the state in action at that time step, because that's the only thing that the difference of logs depends on. So we can actually marginalize out all the other states and actions at every time step. So now this is what we're left with. And that's going to be actually very convenient. So what we're going to then do is a little bit of rearranging. We're going to take this negative p bar term, we're going to leave that alone. And then for this other term, we're going to rewrite it as the expectation under p of x, and then the expectation under pu given x, right? Because it's an expectation under p of x comma u, so we can write p of x comma u as p of x times p of u given x. And then we can just separate out those two expectations. And this term right here, this is just the negative entropy of p of u given x. So that's just the definition of entropy, expectation under p of u given x of log p of u given x. So now we just have the expectation under p of x comma u of the negative log of p bar minus the entropy of that controller. This term, the p bar, doesn't depend at all on the new controller in any way. It's just some cost. And this is its entropy. So that's the equation we came up with. And we saw before, on that previous slide when I talked about linear Gaussian controllers, that LQR can be shown to optimize this objective, the maximum entropy objective, if we use the linear Gaussian form. So the only thing that differentiates these two equations is that here we have negative log p bar, and here we have c. So we can just set negative log p bar to be c, and LQR can actually optimize this kind of KL divergence. And that's going to be awfully convenient. So provided that, of course, the new controller is given by this equation. So if we can get the KL divergence into a cost, then we can just use LQR. But it's a constraint, it's not a cost, so we're not quite done yet. So we've shown that we can stuff a KL divergence into a cost function and solve it with LQR, but we want a constraint, not a cost function. So how can we put something in a cost function and still use it to impose a constraint? And that's the and to answer that question, we're going to have a little digression into a little bit of convex optimization math, which for some of you maybe is going to be a review, but it's actually super useful and pretty cool to know about. So I'm going to have a little digression to tell you about something called dual gradient descent, and then I'll tell you about how we can use it to impose this constraint by just adding a term to the cost function. So for discussing dual gradient descent, we're going to back up and have a much simpler optimization problem just so that we're not cluttered with lots of ugly notation. So we're going to have sort of the prototypical constraint optimization problem. Minimize f of x subject to some constraint c of x equals 0. And then we'll go back to trajectory optimization once we're done with this. So from convex optimization, we know that we can write down something called a Lagrangian, where we have the objective here, and we have a constraint with a Lagrange multiplier. And then from the Lagrangian, we can write down the dual function, which is a function of just the dual variable, which is just the minimum of the Lagrangian with respect to the primal variables. And then we know that if we maximize the dual, we get the resulting Lagrange multiplier. We plug that in here, and then we solve the minimization with respect to x. We'll actually get a solution to our constraint optimization problem. So this is sort of the chapter 1 for convex optimization. So how do we maximize a dual function with respect to dual variables? Well, one way we can maximize a function is by computing its gradient. So let's do that. Let's compute the gradient of the dual function. For simplicity, let's use this x star of lambda to denote the x that you get when you minimize the Lagrangian for a given value of lambda. So we can kind of say that the optimal x for a given value of lambda can be expressed as a function of lambda. So hence, I can write the dual function as L of x of lambda comma lambda. And then we can just write down the gradient of the dual function. We have two terms, one where we differentiate through the first argument, and the other for differentiating through the second argument. So for the first argument, it's dl dx, dx d lambda, and the second one is just dl d lambda, right? Now, if x is the x that minimizes the Lagrangian, then sort of by definition, dl dx is going to be 0, right? Because if x is the value of x that minimizes this thing, at the minimum, the derivative is 0. So that means that this term is actually going to go away if x star is really the value of x that minimizes the Lagrangian for some value of lambda. So that's what we're going to use. We're going to use the fact that that dg d lambda is actually just dl d lambda for when you plug in the x star that actually minimizes the Lagrangian. And that's the critical thing that makes this algorithm work. So the dual gradient descent algorithm just works like this. First, you find the value of x that minimizes the Lagrangian for the current value of lambda. Then you compute dg d lambda just with this equation because you know that the other term has vanished because your x is minimizing the Lagrangian and therefore its derivative is 0. And then you just take a gradient descent because we're maximizing. And that's it. So this is the dual gradient descent algorithm. It's an iterative algorithm that computes the dual variable, and then you just plug in that dual variable, and you get the solution to the constraint optimization. Does anybody have any questions about this procedure? Yes?
Except your first step has to be such that, usually you'll use gradient descent, which doesn't give you always like somewhere where the gradient is.
Yes. Yeah. So choosing this step size can be a little tricky sometimes. You choose a small value. If you have just one dual variable, one of the things that works really nicely is to just do a bracketing line search. All right. So now let's put the pieces back together. So we have this dual gradient descent procedure. We saw before that we could plug in the KL divergence into the cost function for LQR. So now let's combine these two ideas and actually solve a constraint optimization problem. So this is the constraint problem we want to solve. Minimize the expected cost with respect to the new controller subject to this constraint on their trajectory distributions. We saw before that the KL divergence between trajectory distributions simplifies to this really nice thing, which is just the entropy of the new controller and the negative log probability under the old controller. So now we can write down the Lagrangian of this problem at the top. It's a little bit messy, but actually not too difficult. So here is our cost. I've just expanded out this term in here. So we have lambda times log p bar. So that's just this term. We have lambda times the entropy. And then we have the epsilon. So we have to do dkl minus epsilon. So that's why we have lambda times epsilon here. So here all I've done is I've just taken this definition of KL divergence, plugged it in here, and written out the Lagrangian. And then I just distribute the lambda inside the sum. So this is the Lagrangian of this problem. This term at the end here doesn't depend on anything that doesn't depend on the controller, but it does depend on lambda. All right, so that's our problem. And now, this is the dual gradient descent procedure that we'd like to apply, right? We want to find p star that minimizes with respect to p the Lagrangian, compute the derivative with respect to lambda, and then increment lambda according to the gradient descent rule. There's only one lambda because there's only one constraint. So this is exactly dual gradient descent. And the tricky bit, of course, is this one. We need to actually perform this minimization. And here's how we're going to do that. So remember that the linear Gaussian solution solves this kind of problem, so minimize cost minus entropy. We actually have this kind of problem. So what we're going to do is we're going to first divide everything by lambda. That's OK, because if you divide by a constant, then the optimum doesn't change. So we divide everything by a lambda. And now we have 1 over lambda times the cost, this term, and then the entropy is just like we had up here. So these are all good. So now we're just going to use LQR, but with a different cost function. The cost function is going to be 1 over lambda times the old cost minus log p bar. So if we take this as our cost, that just substitutes in here, and we see that the regular LQR algorithm just yields us a solution. So that's it. So we're just going to do this to find the p star, and then we'd use gradient descent. So we set our cost to be the surrogate cost, use LQR to find p star, increment lambda according to some step size times the constraint violation, and then repeat. So this will get us a new controller where the resulting trajectory distribution is within some epsilon of the old trajectory distribution. So this is for linear Gaussian controllers. For more complex neural network policies, we'll see how we could do this later on in the course. But this we can use for the local models method. And that'll keep us close to the old policy. So yeah, so beyond just dealing with local models, bounding KL divergence between two policies or controllers, whether they're linear Gaussian or more complex, is really useful in general to control how much you change if you're using some kind of approximation or linearization. And bounding KL divergence between policies is equivalent to bounding the KL divergence between trajectory distributions, as we saw from that derivation. That actually holds whether or not your policy is linear Gaussian. So that actually holds for general policies. And we'll use this later for model-free RL as well. So just to conclude, in the last minute, I'll show you one last case study for today's lecture, which is actually using this method to control some physical systems. So this is basically the algorithm that we've derived with local models. And we can see here the learning process. So this is a robot that's what it's doing is when it moves its arm every five trials, it refits local linear models at every time step to those 5 trials. In this case, using a Gaussian mixture model global model. Updates its policy using the KL divergence constraint formulation, and then executes the new updated policy. So every 5 trials is doing this. and in this case, it's learning to stack these little Lego blocks. Here's a video of it kind of a few trained controllers doing a number of different manipulation tasks. So these are all trained using the same algorithm, just using the local model stuff. There's no deep learning at this stage. We'll talk about how to bring that in the next lecture. But for now, this is just showing kind of the different unknown dynamics systems where this can work. The state space here is the positions of all the joint angles, as well as the end effector and their time derivatives, their velocities. And the actions are just the torques on the robot's arm. So that's kind of showing some of the results. And then we can look at some learning curves for these algorithms, so we can see how many samples they need. These local model-based methods in general are actually pretty efficient. So with the local models, it's kind of tens of samples to get most of these behaviors. OK, I'll go through the other case studies in the rest of this lecture on Wednesday. So I'll see you all then. Remember to check the new assignment will be posted later this afternoon, and the final project assignment has already been posted.